let me take a little bit of time and just review the few key points that we covered the last time. If you remember, we talked about random processes. And we discovered when you talk about random processes, you actually have two dimensions that you're concerned about. One is the amplitude dimension, saying what is the distribution of this process in the amplitude domain. And then when we characterize the process in the amplitude domain, what we usually give is PDF of the process. Let's say this is a random process x of t. So you're going to have PDF x of x, which will give us the distribution of the process in the amplitude domain. This is not the only way how you can specify it. You can specify it through CDF, you can specify it through moments. There are a couple of equivalent representations of the random process in the amplitude domain. But PDF is the most common, and it's self-sufficient. If I give you PDF, I've told you everything you need to know about the random process in the amplitude domain. Now, the second dimension that we're concerned about the random process is how does it evolve over time? And this is a time domain. And the way how we said we're going to characterize this random process is by giving the autocorrelation function in the time domain. Autocorrelation function that was defined R of t at a given time t. Actually, we can give this one also as a function of t, right? Because the PDF may change over time, right? How does the signal behave in the amplitude domain may change over time. The second descriptor is the autocorrelation function at the time t as a function of tau, and this was defined as expected value of x of t, x complex conjugate of t plus tau. And we said between these two, we have a full representation of the random process. We have its amplitude characteristics and its time domain characteristics. What we did also last time, we defined something that we call stationary random process. So, stationary process essentially the process is stationary if it is stationary in the amplitude domain and in the time domain both, right? So if the process is stationary, if we have a first condition that is PDF x of t x is just a PDF x of x, meaning that for every t, you get the same distribution in the amplitude domain. It does not change over time. And then the second condition is that R of t tau is essentially just R of tau, where your autocorrelation function does not depend on t either, but just on a separation between the two samples in a time domain. So it's only dependent on tau, but not on t. So that's what we call stationary process. We had a weaker condition that we call wide sense stationary. Here, we also have two conditions. One condition is this R of t tau is just R of tau, right? So autocorrelation function does not change. So the time domain characteristics is unchanged as a function of time. But here we have a weaker condition where we require that mu of t is just equal to mu, and sigma squared of t is equal to just sigma squared. So we are requiring that the first two moments of the process do not change over time. Its mean does not change, and its power does not change, but the rest of it may change, right? So this implies that all moments stay the same. Here we're just looking at the first two moments and saying first two moments are constant over time, and the autocorrelation function is constant over time. That if that's the case, then we call this process wide sense stationary. Why is this an important category? Because a lot of our signal processing algorithms and a lot of our, I guess, analysis in general requires that the mean value of the signal and the power of the signal stays constant for us to do something, right? And we rarely pay much attention to the higher order moments. There are algorithms where this is also concerned, but in most of the algorithms that we deal with, especially when you talk about signal to noise ratios and those kind of things, then you really just talk about the powers, the ratios of the powers, and it's important to say powers do not change over time. Powers are stationary, and this is, as I said, weaker condition that's satisfied obviously more times than this stronger condition here. This is a very strong condition. You require that the entire PDF does not change over time. Nevertheless, some of the most important processes that we deal with are kind of stationary. Like if you look at, for example, noise, which is going to be a process of highest concern to us, it turns out that under some relatively nominal conditions, the noise can be treated as a stationary process. So that's the definition of the stationary. The second type of processes that we have to shed the light on are processes that we call ergodic processes. So let's define what ergodic means and kind of see how you divide all of these random processes into all of these different categories. So ergodic processes. Consider a random process x of t. That's our random process. And then we have a function g of x, which is a function of the random process. We can define two kinds of averaging in in general. This is like a general statement. And in other words, we can take this process and average it over time, or we can average across all the possible realizations of the process. First type of averaging, which is the one that we call ensemble averaging. What is ensemble averaging? Well, this is what we, I'm going to start here. I'm going to be looking at all possible realizations of the process. So let's say this here is the first realization of the process, but I'm not only looking at the process itself, I'm looking as a function of that process. So let's say g x1 of t, right? So I'm taking the first realization of the process, x1 of t, and I'm applying some function to it. In the most trivial scenario, g can be just mapping the process onto itself, right? G of x is equal to x. But it can be, for example, g of x can be x squared, in which case I'm looking for the power of the process. It can be absolute value of x, it can be sine of x, whatever that function may be. This is time. Now, I can look at the second realization, and this is now slightly different, g x2 of t, and so on. In general scenario, you have infinitely many of these realizations of the process. What are we talking about? Let's say the process is voice as a category of the random process. Then these x's are everything that everybody has ever said, right? All possible realizations of this process. And let's say g is, let's say, squaring of that process. So I'm looking at the power of across all of these possible realizations. If I specify a time, let's say this is the time t0, then I can define ensemble averaging as expected value of g of x of t equal to t0, right? I'm looking at what is the expected value of this random variable. I froze time t0. Every one of these samples here is a value of this function g of x at t equals t0. Obviously, if I look across all possible realizations, they form a certain PDF, and then I can take expected value as the expectations across these values that are forming this PDF. So this becomes integral when x goes from minus infinity to plus infinity, g of x times PDF of x when t is equal to t0 dx. Right? This is called ensemble average. If the process is stationary, then this t is irrelevant, right? This t0 is irrelevant, meaning that wherever on this t-axis, wherever I make a cut, I'm going to get the same PDF, therefore I'm going to get the same expected value, right? So for stationary processes, we can draw this at t equal to 0 and get the expected value of g of x is equal to integral when x goes from minus infinity to plus infinity, g of x times PDF x of x dx. Because PDF of x is now only function of x, not function of t, right? Because it's the same for every t. Now, what is the practical obstacle in using this kind of average? The fact that you need to have all possible realizations, which is practically impossible, right, because of this set is infinite. But even to get a good approximation, you need to have large numbers of them. Let's say I don't want to do all of them because I can't, but I do 1,000 or I do 2,000 or whatever needs to be the case to get enough sample large enough so that you get convergence in the statistical sense, right? Now, and a lot of times you actually have no choice. This is how you need to do it, and you just figure out a way how to accomplish the task. However, there is a class of processes for which we have an easier way out. So let me talk about time domain average. Time domain average. If I have, let's say, the starting point is the same. I have my realization x1 of t, and this is a g x1 of t. So one realization of this random process. Then I can define a time domain average, g of x, as a limit when t goes to infinity, 1 over t, integral over t, g of x, actually no need for 1, just g of x of t. Okay? This is something that is a good friend of ours. This is what we encountered before, right? This whole operator limit, 1 over t, integral over t, we know that this represents the time domain averaging. We used it before to define the power of the signal when signal x of t was a deterministic signal. Now here, the x of t is not a deterministic signal, it's a random process, or more precisely, it is a sample realization of the random process. Now in general case, if you do averaging this way, and you do averaging this way, you're going to get different results, right? There's nothing that says that these two need to be the same. However, in some special cases, so in general case, expected value of g of x is different than this value. Right? There's nothing that says that if I average across all possible realizations, it is the same as the averaging over time. However, in a special case, these two may be the same. When that's the case, the signal or the process is called ergodic. Okay. Now the question is, okay, all of this seems quite abstract, but let me, before I go and give you some examples of when the process is ergodic, let me clarify the benefit of this. If the process is ergodic, what that means is I don't need multiple realizations of the process. I need a single realization of the process from which I can determine all the possible averages that I need. So let's say this g of x is just x. By doing this, I'm determining the average value of the process. If g of x is equal to x squared, then I'm determining the power. G of x equal x cubed, I'm determining the third moment, and so on. So I can assemble my entire PDF just by looking at single realization of this process. From the practical standpoint, this is of a great value to us, because all I need to have is long enough realization of this process to be able to statistically describe this process complete. Let me spend a couple of minutes. I didn't put that in the notes, but I'll just give you an example of first the process that is not ergodic, so that you understand intuitively what that means. And then I'll give you an example of an ergodic process, so that you see why these two averaging essentially give you the same result. So example one, this is non-ergodic process. Let's say we're having a group of students that are working on an electronics lab, right? An electronics lab, and they all have their power supplies. And let's say they all leave room for getting to turn off their power supplies, right? And what happens in that case, if I now look at all the workstations, and let's assume for a moment that somewhat unrealistically that there are infinitely many students, right? So just not bounding the count this way. First student left voltage at this point, right? The second student left voltage at that point. The third student left voltage at this point. So this is, let's say, V1 of t, V2 of t, Vn of t, and so on, right? You can see that the voltage that is left on a power supply is going to be a random variable. It's going to take some value between, let's say, minus 12 and 12, because that's a typical voltage for a power supply. Now, that random variable is going to be different on any one of these generators, these power supplies. If I fix time, first of all, is this process stationary? Does it change over time? No. If I fix time at any place, I'm going to get the same statistics across all of these amplitudes, right? Now, if I look at this time, t equal t0, what is the expected value of v? What is the expected value across? What is the average value across all of these? 0, right? So I expect to see 0, on average. Some people are going to leave it positive, some are going to leave it negative, some are going to actually make it close to 0, or whatever it is that they left when they leave the room, right? Now, that's the average across all samples, right? Now, let's take a look at average across every one of the samples. If I pick a random sample, you can see that the average here across the sample is going to be different than average across all the samples, right? So this is an example of non-ergodic process. If I pick one particular realization, the probability of having the same kind of average as across all possible realization is 0, right? You follow so far? This is averaging across the samples, an ensemble of realizations of this process. This would be averaging across the time, and they give me a different result. Let's look at an example 2, which is an example of average. Example 2. This is ergodic process. Consider a mind experiment where I have, let's say, many different resistors that are all having the same resistance value. Okay? They're all having the same resistance R. And what I do, I have a very sensitive voltmeter that I put here on the edges of all of these resistors. And I'm measuring the voltage that is happening across these resistors. Since the resistors are not at a zero temperature, there will be random motion of the electrons going through them. And as a result, at the ports here, there will be some difference in the potential. There will be some voltage. And that would look somewhat like this for the first resistor. So this would be V1 of T. It will look somewhat like this for the second resistor. And so on. Now, let's take a look at averaging in this case. If I freeze time, first of all, if the temperature doesn't change over time, that this process is obviously stationary, right? Because the statistics will not depend on any given time t0 that I choose, right? If I choose here and here and here, I'm going to get the same statistics across all possible magnitudes. But now let's say, what would be expected value of V of t if I do the averaging across all possible realizations? 0, right? There is no DC current, so the voltage has to be 0. If I pick one of these, what do I get? What do I get as an average? 0. So, and this would be true for every one of the moments. If I square all of them, and I take the average this way, and I take the average this way, I'm going to get the same result. If I cube them, if I take any moment, I'm going to get the same result. So this is an example of the ergodic process. Now, how do you intuitively see if the process is ergodic or not? What is kind of, this is not scientific, this is how I explain it to me myself when I studied this, and it kind of worked through my life. If you can take one of the realizations, and imagine I observe this V1 of t for a very long time, and then I take scissors and I start cutting pieces of it, right? And then I take these pieces and put them underneath. If that picture is indistinguishable from this one in a statistical sense, then I have an ergodic process. Strictly speaking, ergodic process kind of goes through all possible realizations of the process in a single one realization. If I monitor this V1 of t for a long time, it will actually get portions that look exactly like these portions that I'm lining up one underneath the other. So that kind of process is an ergodic process that you have, and for these kind of processes, averaging across the time and across the ensemble give you the same result. So we have kind of covered several types of processes so far. So let me draw a picture here. Say this is all random processes. Of all possible types, right? We have defined a class inside them that we call wide sense stationary. How is wide sense stationary class defined? You have a process for which first two moments in the amplitude domain don't change over time. The process has the same mean over time, the same power of the time. And autocorrelation function does not change over time. If that's the case, the process is called wide sense stationary. If you have a wide sense stationary process, but you have not only that the first two moments don't change over time, but the entire PDF does not change over time, then you have what we call stationary process. Strictly stationary. and then subclass of the stationary processes for which I can obtain the averaging, either doing it in the ensemble domain or doing it in the time domain, are called ergodic. So these are my ergodic processes. Okay? Now, this scale here is arbitrary, but you can kind of, what is important here to realize the relationship. If the process is ergodic, it is automatically stationary, it's White-Stein stationary. But if the process is stationary, it doesn't have to be ergodic, or if the process is White-Stein stationary, it doesn't have to be ergodic, right? So kind of realize this relationship. What we're going to be dealing the most with are these processes. You know, because they're analytically the easiest one to deal with, and this is an introductory course. So we're really dealing with the concepts. And it turns out for what we are trying to do here, it's fun, right? Because most of the applications that we deal with are kind of falling with dealing with the processes that are falling within this category. Or if not within this category, then there's something special. They may have some other properties that we can explore. There's something called cyclostationary processes that are kind of encompassing this and so on, but we're not going to go into all of these details. So from now on, when I deal with the random processes, unless I specify explicitly, which I don't think I'm ever going to do, we're talking about stationary ergodic processes. And I'm not going to be repeating that. Maybe every now and then I'm going to say it. But what that means, I'm going to be freely taking the averaging either in ensemble domain or in the time domain, whichever one is more appropriate for a given situation, right? Just be aware of that. Most of the results that we're going to derive are going to be general in scope and widely applicable. But if there are some cases where I have to explicitly evoke this ergodicity, I'm going to point it out, because then they may not be valid in a general case. Right? Okay? Go ahead.
You said it's when it's stationary, so it doesn't really depend on time. But the example that you gave for the resistors is non-stationary, but it's still.
No, this is stationary. The process is stationary. What does not depend on time? Let's take a look at time t0, right? There's infinitely many of these resistors, right? So now I cut the time, and what I do is I record the samples at any given time. That sample becomes a random variable. And then the random variable, whenever I say random variable, just when there are these triggered responses, like when you say periodic Fourier series, when I say random variable, the immediate thing is PDF, right? The random variable travels with its PDF, right? The PDF is what describes the random variable. It's kind of like a driver's license or something that is attached to a random variable. So here's the PDF that I obtained for this random variable. So this is PDF of this voltage at the time t equal t0, right? Now, I change time, and I look at now this different time, and I do the same experiment. I determine again PDF, right? Now the way I draw it is probably not good, because I draw them that they're different, but what I wanted to say is, in this case, think about the reality of the situation. If these resistors stayed on the same temperature, what would be the reason for this PDF to change? There will be no reason, right? So the PDF is the same, right? So that's an example of a process that is stationary in amplitude domain, right? This process is stationary in amplitude domain because the statistics of the amplitude distribution does not change over time, right? So this process is stationary in amplitude domain. This process is stationary in the amplitude domain too. If you look at the PDF, let's say it is T0, it is probably uniform, right? Because anybody could have left any voltage in between -12 and 12 volts, right? So at this time it's the same, at this time it's the same, at every time it's the same. So this process is stationary in the amplitude domain too. So both of these are stationary. They both belong to this class of processes, right? They're both in this setting. But the first one is here. So that's the first process, right? Why? Because it is stationary, but it is not ergodic. Why it is not ergodic? Because if I average across the amplitude domain and I average across the time domain, I'm not getting the same result, right? The second process is here. Because that process is stationary, its statistics does not change over time. But all the averages that I can come up across the ensemble and all the averages I come up across the time are going to be the same. Therefore, you know, if the continuation of this mind experiment would be, I cut this way, and then the other one is, I don't really cut, I just look at one of these realizations and I form the histograms of the values that this realization goes through. This histogram is going to look exactly like this, right? And then I said, well, how you build your intuition? The intuition is if I look at this process and I take my scissors and cut it into pieces and line it up, one underneath the other, I actually get the same as if I were looking at the different realizations of the process. So that's my ergodic process. And a lot of processes are like that, right? In theory, we treat voice like that, right? Or at least discourse. In theory, if I continue speaking, right, forever, I'm going to say everything that everybody has ever said, right? Random, just, you know, if you listen to me long enough and I just babble, there will be, Obama's inauguration speech, and there will be, whatever is being said, right? So I'm going to go through all of that over time. So I can cut these and put them underneath one another and actually get all possible realizations of the voice signal that has ever been, right? Okay. So this is, so let's put some of these things to practical use. Place it on something wet. Okay. Let me first define two quantities that we care about. One is the power, and the other one is the energy of the random process. So power and energy first, let's take a look at energy. These are straightforward extensions of how we define the energy for aperiodic signals. It's just that here we're dealing with the random processes. So the way how we define it, we look at the random process that has different realizations. So energy for the first realization is going to be integral when t goes from minus infinity to plus infinity, x1 of t squared dt. Energy for the second realization is t goes from minus infinity to plus infinity, x2 of t magnitude squared dt, and so on, right? You have infinitely many of these realizations, so you can calculate, at least theoretically, what these energies are for each individual realization. You can see now that this E1, that this energy here, is yet another random variable, right? It maps all of these realizations into a single value on the real axis. Well, the energy of the process is going to be defined as expected value of this random variable energy here, which is expected value of this function here, integral when t goes from minus infinity to plus infinity, x of t magnitude squared dt. Now, if the signal is ergodic, then all of these will give you the same values, right? So for ergodic signals, I don't have to do this averaging across all possible realizations. The realization for a single one will be the same, right? Will be sufficient to determine what the energy of the signal is. The power is defined very much the same way. I can say P1 is a limit when t goes to infinity, 1 over t, integral over t, x1 magnitude squared dt. And I can kind of do that for the second realization, which is the limit when t goes to infinity, 1 over t, integral over t, magnitude x2 of t squared dt, and so on, right? I do have infinitely many realizations. So the power here, let me call this E actually, so that it's distinguished, is going to be expected value of this power, which is expected value of this limit when t goes to infinity, 1 over t, integral over t, x of dt. And again, the same story. If the signal is ergodic, then I can actually just do averaging across one possible realization and get the same value. These PIs, P1, P2, P3, all the way to infinity, are actually all going to be the same, right? Because the signal is ergodic, right? So averaging across all realizations gives me the same result. Okay. So we're going to be working with these, as you imagine in our world, power and energy are very important quantities when it comes to signal description. So let's now look at, I think with this, I have kind of covered everything, well, except for one thing, that I need to describe the random processes. What is of most importance to us is what happens when you present this random process to the linear system, right? Because our communication system we're going to model as a linear system, and what I need to know is what happens when the random process is presented to that linear system. So this is a random process and linear systems. So this is the settings that we are concerned about. You have input, which is x of t, which is some form of random process. So far we have all of these descriptors that are given on the upper portion. We haven't looked what happens to this random process on the other side of the mirror, right? We're looking at still everything I've covered so far is in this world, right? I'm looking amplitude and time. Later on we'll look what happens on the other side in the frequency domain. How do we characterize the random process in the frequency domain? But so far I'm presenting some random process x of t. I'm presenting it to a linear system, which I know can be characterized with its impulse response. And I'm getting some output y of t. Okay? What is it that I can immediately, that I know about this y of t? First thing that I know is for every realization of x of t, I can calculate y of t as x of t convolved with h of t, right? That's very self-evident. If I pick a realization of this random process, particular speech or particular signal that comes out of this process, and I present this to a linear system, I know that what comes at the output is going to be convolution between your input and the impulse response of the system. So for every given x of t, I have no problem calculating y of t. That's fine, but it's not very useful, right? What I want to know is this. I have some descriptors of x of t here, and I have h of t. What are the descriptors of y of t? Can I take this PDF here and determine what is the PDF of y of t? Can I take the autocorrelation function for this one and determine what the autocorrelation function of this one is, right? So that's what we are after. So let's look at some other results that we can state at this time. The second result is if x of t is stationary or even more so ergodic, then y of t is stationary slash ergodic. The linear time invariant system cannot change stationarity or ergodicity of the process. So if this, or if what happens on the left-hand side, for example, does not change over time, then what happens on the right-hand side does not change over time either. Why? Because it's a linear time invariant system. So the system processes the data always the same way. Therefore, if it's stationary on the input, it is stationary at the output, right? If it's ergodic at the input, it's ergodic on the output as well. And then the third one that can be also demonstrated relatively easy, but it takes a little bit writing. The relationship between autocorrelation functions is given by Ry of tau, that's the autocorrelation function of the output, is going to be Rx of tau convolved with h of tau convolved with h of minus tau. Okay, that's a very, very powerful result. It's actually relatively easy to derive. I'm just not, let me just tell you how one would do that. You would say R1 of tau is equal expected value of y of t, y complex conjugate of t plus tau. And then you would replace this y of t as a convolution. So this becomes expected value of integral, let's say when mu goes from minus infinity to plus infinity, h of mu, x of mu, h of t minus mu, d mu, and then times integral when nu goes from minus infinity to plus infinity, x of nu times h of t plus tau minus nu d nu, and then complex conjugate this. And then, you know, from here you change the order of integration, and in a couple of steps you can actually demonstrate that this holds. Right? So these are the three properties that I want to point out here. Now, what is missing, and this is an important thing that is missing that we need to define, is this bottom piece. I need to understand, how do I characterize my random process in a frequency domain, right? You see that that part is missing, right? We know how to do that for deterministic signals. How do I characterize deterministic signal in a frequency domain? Taking the Fourier transform of the signal itself. So that part is missing here for the random processes. I need to understand what sinusoidals do I need to use to build a particular random process. Now, this one I'm okay. I know that to the impulse response, I can attach the frequency response, which are Fourier transform pairs. And then I need a descriptor here that tells me how do I characterize my output random process in a frequency domain. Let me just ask you now blindly, you know, this is, you haven't seen this before, so let me see what's your intuition. I've shown here, for example, that autocorrelation function and of the input and output are related through some sort of convolution, right? You see that autocorrelation function of the output is autocorrelation function of the input and convolving with some impulse response. Now, if I come up with a frequency domain descriptor here, that is a counterpart to the autocorrelation function, what do you expect to see at the bottom? When you look at convolution in the time domain, what's the image of that for the frequency domain?
It's an omega.
multiplication, right? So this is what I expect to see, and we'll see how we get there. But I expect to see that once I go from this time domain into frequency domain, there will be some relationship where whatever is the equivalent representation of my random process in the frequency domain on the input and the equivalent representation on the output are going to be related somehow through product with this frequency response, right? That's what my gut tells me, right? So let's go formally and see how we actually get there, right? But that's where what we expect to see based on our knowledge of what happens with deterministic signals. So how do I define the frequency domain representation of the random process in a frequency domain representation of the random process? We're going to define a quantity that is called power spectral density of a random process. Now all of these DFs and so on. This one is called PSD. PSD stands for power spectral density. Okay. This is going to be our representation of the random process in a frequency domain. Let me formally define it, and then what I'll do is I'll tell you intuitively how you should understand this, right? What is the meaning of this power spectral density? How do we define that? Well, we're going to start by saying x of t is a random process. Now, random process as such is usually not an energy signal, and some of them are, but a lot of them aren't. For example, if you look at noise, it goes forever, so it's a power signal, right? If you listen to me talking, it goes forever, so it's a power signal too. So in order to formally define this power spectral density, we're going to do the same trick that allowed us to determine the Fourier transform of, or similar trick that allowed us to do the Fourier transform of a deterministic signal. We're not going to look at the realization of the process as a whole, but we're going to look at its truncated version. And the truncated version becomes an energy signal, so it has a Fourier transform. And then we'll say, okay, well, let's look at the truncated version where its duration goes to infinity and see what does that converge to. Okay? So I'm going to define truncated version of a realization of x of t. Now this one is going to be x t of t lambda I for is going to be equal to x of t lambda I when t is smaller than t over 2 and 0 otherwise. So there's a lot of notational things here. I cannot try to use the same ones that they use in your book, but let me explain what is being meant by all of these. So here's the big picture. You start by random process x of t, but more practically, you start with one realization of that process. So this is what they say, this is your x of t lambda I. This is I realization. Okay? If you remember our original concept here, this is the I point in the sample space where all possible realizations of the process reside. Now, instead of looking this whole thing, I'm going to, let's say this is 0, I'm going to look at an interval that has a duration of t. So this is just the duration of t. And I'm going to define a signal that looks somewhat like this. It is 0 outside of this interval. Then within this interval, it's the same as this signal. And then outside of the interval, it becomes 0 as well, right? So that's my signal x t of t for a given lambda I as a realization of this. Now, I can define this for every possible realization of my random process, so there's infinitely many of these truncated versions, each one of the duration equal to t. So let's pick these versions. I'm going to kind of line them up here. And let's just, this is t, t, t. And this is my duration of capital T. So this is xt of t lambda 1. This one is here xt of t lambda 2, x capital T of t lambda n, and so on. There's infinitely many of these guys. Each one of them are made 0 outside of this interval, and then inside the interval they kind of have certain behavior. Right? Whatever they may look like, right? So these are the truncated version. Now, what I do next is since each one of the truncated version now becomes an energy signal, it has a Fourier transform. So I can take the Fourier transform of this signal, of each one of these signals, but instead of plotting the Fourier transform, I'm going to plot something that is going to be magnitude of the Fourier transform for the lambda 1 squared divided by t. So this is going to be the first one. This is going to be the second one. Let's say it may look somewhat different. So this is x of f lambda 2 magnitude squared divided by t, and so on. So this is x of f lambda n magnitude squared divided by t. So how do I get here? Well, I take each one of these truncated versions, I take its Fourier transform, square it, and then divide by t. What is it that I'm actually doing here? Remember the interpretation of the Fourier transform. It gave me the sinusoidals that are participating in building of this particular waveform, right? So here, I'm getting the distribution of the power between sinusoidals that are building this waveform. I'm getting distribution of powers that are building this waveform, distribution of the powers that are building this waveform, right? And I get, all of these for all of these different distributions for all of these waveforms that I have here. And now I'm going to look at a single small frequency band here. And then I'm going to average all of these. So as a result of that, I end up with one frequency domain representation that is going to be expected value of x of f lambda divided by t squared. So I'm going to take the average across all of these Fourier transforms to obtain one single one. And then what I'm going to do is I'm going to define my S x of f, power spectral density or power spectral density x of f, as a limit when t goes to infinity, 1 over t times x of f. Actually, I should put t here. These are all index t, right? Xt of f lambda magnitude squared. And this is what I call power spectral density. What is the meaning behind the power spectral density? Well, if you look at what is the meaning, how I constructed this, I'm looking at all possible realizations of the random process. Through the Fourier transform here, I'm discovering what are the sinusoidals that are required to build any possible realization, right? What are sinusoidals that I need to build this? What are the sinusoidals that I need to build this, and so on. And then once I look at all of these possible sinusoidals that I need, then I take the average across all possible realizations. So what I'm getting here is the sinusoidals that I need to build this process as a whole, right? It turns out here I have exaggerated a little bit, right? If this is some sort of ergodic stationary process, then chances are these are going to be very, very similar, right? Because remember, the Fourier transform is also a form of averaging, right? Where I take the, I'm taking an integral transform of my signal, right? So what I do is I will probably get very similar graphs here, and then when I average them, I'm going to get a single function here of frequency that tells me what is the individual contribution of particular portion of the frequency domain to building of this kind of process. This is what we kind of talked about already. We didn't point it out there, but I already mentioned something like this. I already made a statement when I said, when you think about a voice, what is a bandwidth of voice? And we said, well, the voice extends from 0 to 4 kilohertz. What is it that I'm referring to? You know, I'm referring to the power spectral density of the voice. The voice has components between 0 and 4 kilohertz. So the voice, to build a voice signal, I need to use components that are in this frequency range. And outside, the contribution of the sinusoidals is going to be negligible, right? I'm talking telephone voice, right? And that's how it is determined. So far, we haven't looked at voice as a whole. We just looked at if I have a signal that represents voice, I know it's going to be between 0 and 4 kilohertz. That was our message signal M of t. But now I'm extending everything, and I'm looking at a class of the signals, and I'm making a much more powerful claim. I'm saying not any particular signal is made out of frequencies between 0 and 4, but all voice signals can be built out of these frequencies, even though they are different things that different people say and different, in different voices. It turns out statistically they are all built out of components that are between 0 and 4 kilohertz. That's the statement of this power spectral density. And if I say power spectral density of the process looks like this, let's just look at this as now not general, but as an example, then you can say, oh, this process is predominantly around DC. It is slowly varying because it has a high dominance of these low frequency components. They participate more, right? Because this power spectral density is larger there. And then there is some variability on the top because the signal has these higher frequency components as well. But this variability kind of becomes less and less powerful as you move away in the frequency domain. So this process is kind of predominantly slowly varying process that has some noise on the top of it as a result of these tables, right? All of this I'm kind of concluding from this graph of a power spectral density, because it tells me what sinusoidals are required to build this particular process. Any questions here? These are a little bit abstract concepts, right? This is not as straightforward. You have to spend some time thinking, right, about it. And what I'll do is let me go through, we're going to cover one theorem, and then I'll kind of go through a couple of examples that shows us how do we actually use this. Because really, this is really, really powerful, right? Once you go through this course, you're going to actually learn how to think in those terms, right? And to start relating what you see in the frequency domain to the behavior of the signal in the time. Go ahead.
I have a question. When you come up with a final sketch of the spectral output, what does the lambda become? You have lambda 1, 2,
There's,
3?
actually, lambda goes away. Lambda is across all possible lambda,
Okay.
right? So I'm taking, think about this goes forever, right? So I'm taking, let's say, one component here. I'm looking at this is some value 5. Let's look at the same component. Here it's, let's say, 4. Here it's 3. Here it's 1, and so on. So I take all of these numbers, average them, and this produces one number here, 4.3, right? Then I do the same across all possible values, right? And I aggregate this one graph. And what does this graph say? This is the relative contribution of this frequency in building of all of these signals. Some of them will use it more, some of them will use it less. But chances are, if my signal is ergodic, they're all going to use it about the same amount, right? Just that, because this signal will actually have these signals as a part of it anyway, right? So now what I end up is with one plot that tells me what is the relative contribution of the various spectral components in building of this particular signal, right?
One more question. Are you able to combine different types of signals like an exponential, sinusoidal, pulse?
You have to be careful here. We are not talking about deterministic signals. All the signals you quoted were deterministic signals. We're talking about the random processes.
Okay.
So they're not pulse versus sinusoidal versus, these are all deterministic that I can give you a formula for. These are, I'm looking at the noise, I'm looking at the voice, I'm looking at the activity of the sun, or I'm looking at number of electrons jumping from whichever orbit to whichever orbit. So these are the random processes that I'm looking. And then they all exhibit some time domain behavior and some amplitude domain behavior. And what I'm saying, okay, well, how do I characterize that in a frequency domain? And then through this gate-away Fourier transform and through this process, I obtain it this way. Now, the bitter truth about this definition, it is really hard, It takes me time to describe it. I purposely go through it because I want you to understand where it's coming from and what's the thinking here. But from the practical standpoint, it's useless, right? You cannot do this. You cannot compile all. I mean, you can, but it's very hard. You cannot compile all possible noises and then take all possible Fourier transforms and then do that every time you double T. You can't. It will take you a lot of time, and we really need a better way of doing this. So that better way is actually provided by a very powerful result, and that's called Wiener-Kitching theorem. So let me state that theorem, and you will see how everything falls in really nicely into place. So this is one of those points in the class where I say, if we were in a circus, this is the main act. Right? This theorem is one of the, when it comes to describing stochastic signals, this is the main theorem, the central theorem. So, Kitching theorem. Here it is. It's amazingly simple for what it represents. So let x of t be a random process with autocorrelation function Rx of tau. Fourier transform of Rx of tau is Sx of f, right? Where Sx of f is the power spectral density and at this point you should say, well, duh, it should have, you know, it is kind of, I expected to see that, right? Because you have this intuition that when you have a time domain characterizer of something, and then there is a frequency domain characterization of the same thing, they're related to a Fourier transform. We already talked about autocorrelation function as a way how we characterize the random processes in time domain, right? Well, if the power spectral density is to be something that characterizes the same process in frequency domain, then expectations are that these two are related through a Fourier transform. Let me look at an example here. Let's consider a random process x of t. And let's look at the random process that has autocorrelation function given e to the minus magnitude of t over capital T for every tau, right? Magnitude of tau over capital tau for every tau. This autocorrelation function looks like this, right? It is like this, Rx of tau, and then when the value of tau is equal to t, the autocorrelation function is 1 over e of its value at point tau equals to 0. So what does the power spectral density of this process look like? Sx of f is going to be Fourier transform of Rx of tau, and this is a table Fourier transform. You can look it up in a table, but you obtain the result that is 2 times t over 1 plus 2 pi f capital T squared. So that's the Fourier transform of this exponential. Let's consider 2 cases. In the first case, I'm going to look at an example when capital T is small, and in the second case, I'm going to look at an example when the capital T is large. And let's discuss the meaning of those 2. So first example, A, t is equal to 1. So how does the autocorrelation function of this guy look like? It is relatively narrow in time, right? If this is 1, this is R of tau, and when tau hits 1, then this is 1 over e of its value. Okay, so that's a autocorrelation function when t is equal to 1, right? Because it kind of goes relatively quickly, meaning that the autocorrelation function goes towards 0 relatively fast. Now let's catch the power spectral density of this function. So this is S x of f when t is equal to 1. This one looks like this. Why? Because you can see when t is small, then it takes a relatively large f before what I have downstairs becomes significant, right? So it will look somewhat like this. Let's look at part B when t is equal to 10. Now in this case, autocorrelation function is very slow, right? You need to get to 10 before this falls to 1e of its original value. Right? So this is how R of tau looks like here. It's a very slow in a time domain, but what happens in a frequency domain? This is Sx of f when t is equal to 10. Okay, let me actually kind of sketch what I expect these processes to look like so that we can discuss the implication of these results. This is x t equal 1 of t. This is x t equal 10 of t. Okay. So, if I have a process that has an autocorrelation function which is narrow, which goes to 0 relatively quickly, what does this mean? Remember what R of tau tells me. It tells me how correlated is the value at some point here and the value that is tau seconds away, right? If these values are uncorrelated, that means that the signal changes rapidly relative to this time scale, right? That means that there's a lot that has happened at this time scale, right? The signal decorrelated from its value at this time, right? So if the autocorrelation function is narrow, that means that the signal changes very fast. If the signal changes very fast, what sinusoidals do I need to build this particular signal? I need a lot of sinusoidals. I need these small, slow ones, but I also need the fast ones, because in order for signal to move fast, I need, bricks that will, build this signal appropriately. And if I have all the big bricks, I cannot make the small detail, right? So I need a higher frequencies to build this signal. So there is this inverse time relationship that appears here. If the autocorrelation function is narrow, the power spectral density is wide, right? To build a signal that changes rapidly in time, you need high frequencies, and also that signal is going to decorrelate relatively fast in a tau domain. On the other hand, if I have a signal for which the autocorrelation function is slow, meaning that the values for large taus are still significant, that means that the value at this point is quite correlated to the value, that's tau seconds apart. They cannot be, maybe this is not, I'm looking at this, right? So I'm looking at the values that are, quite correlated. So this signal is moving slowly, right? The larger this t is, that means I can look further in the future and the correlation is still there, right? The signal has not changed much. That means my signal changes really, really slow, right? And what happens as a result of that autocorrelation function is broad, but to build the signal that changes slowly, I don't need high frequencies. I need only the frequencies that are focused around the origin. Let's take this mind experiment all the way to its extreme. Let's take a look at the signal that, we'll start from this end, that has autocorrelation function that is constant. Meaning, I have a signal where the value here is correlated to every value that in the future, meaning the signal is not changing, right? What is the power spectral density of this signal? If the autocorrelation function is constant, what do I need to build this signal? Only one component. Which component? DC value, right? So the autocorrelation function that is constant means that the signal never changes, and all I need is the component at the origin. So your power spectral density is infinitely narrow. All I need is one component. Let's take a look at the other extreme. The signal that has autocorrelation function that's delta pulse, meaning that even the smallest displacement of this signal, like I take the smallest step tau, what I have here has nothing to do with what I left, tau away. So what is that signal has autocorrelation function that looks like a delta pulse. How's the power spectral density of that signal? It's constant, right? To build such signal that changes infinitely fast in time domain, I need all possible frequencies, right? And so these are obviously two extremes. All the other signals are going to be in between these two extremes. But the inverse time frequency relationship is always going to hold. If you have a signal that's fast in the time domain, its autocorrelation function is narrow, its power spectral density is broad. If you have a signal that's slow in the time domain, its autocorrelation function is narrow, its power spectral density is going to be, its autocorrelation function is wide. If it's slow in the time domain, its autocorrelation function is wide, its power spectral density is narrow, right? So this is what the intuition that you have to have, right? This is what you need to understand every time, because we're going to be discussing that, and this is going to be central piece of us dealing with the random processes. Because when it comes to random processes, taking one process, one realization of the process is not very meaningful. What you need to be able is to operate with these descriptors of the process as a whole. And we have two kinds of descriptors, actually three kinds now. We have the time amplitude domain through the PDFs, we have time domain through autocorrelation function, and we have frequency domain through power spectral density. Okay? So I'm going to stop here. Let's stop. We'll have to continue. There's a couple more things, but we'll continue later.